to everybody online, welcome to the Game Changer Seminar Series organized by ISI in Bern, where we tackle fundamental questions in astrophysics, heliophysics, earth science, all the disciplines that ISI covers. We bring you the latest results, and we offer the possibility to meet some of the amazing scientists that are doing this science out there. So today, it's a pleasure to have a distinguished colleague and friend, Dr. Emily Rickman, who is actually very familiar with the Swiss environment because she actually did her PhD at the University of Geneva and then continued with the postdoc position there. After that, she moved to Baltimore, where we're really lucky to have her as a fellow of the European Space Agency. And now she's a staff member. Dr. Rickman is a world expert on exoplanet, especially on using radial velocity techniques to characterize exoplanets with the purpose of just eventually identify candidates for direct imaging. So, Emily, I will mute myself and disappear, and you take it away.
Thank you so much, Antonella. I will just go ahead and share my screen. Can you just quickly verify that I'm showing the right mode of slides?
Indeed, you are.
Excellent. Thank you so much. Yeah, thank you so much for having me. Yeah, so I'm going to talk today about how we combine lots of different exoplanet measurement techniques in order to primarily look at cold gas giants. So think of our own giant gaseous neighbors in the solar system like Jupiter and Neptune and Saturn, and how we search for those components in other stellar systems through exoplanets, but also brown dwarfs that are analogs to giant exoplanets. And so I think this is, sorry, there we go. A really good gift to kind of demonstrate that. So I'm going to talk a lot about imaging today, and I'll go into more detail about how we do this kind of science, but I just wanted to show this as a demonstration to begin with. So this is a very famous GIF of a system called HR 8799. And what we see here are 4 planets that are orbiting counterclockwise around the star in the middle there that's hidden behind a mask. And the reason that I want to talk about cold gas giants is a lot of exoplanet techniques really probe this sort of inner region that's very close to the star. So techniques like the transit technique that you may have heard of before through missions like Kepler and TESS, they really target planets that are super, super close to their stars. And those planets are really interesting, and they have a lot of intriguing science and theories that we need to try and understand. But we also need to understand the outskirts of stellar systems in the own way that in our solar system, we have inner planets that we like to understand, but also there's outer planets to build up the overall picture of what we're looking at. And so the imaging techniques that I'm going to talk about today probe more like this region, and this outer circle that I'm showing here is where the orbit of Jupiter is in our own solar system. And so you can see that that is comparable to the kind of orbits that we're looking at here of these planets in this system, and why it's so vital that we use these kind of imaging techniques in order to build up the complete picture of what other stellar systems look like. So on top of that, it's also really important to be able to test models of their masses and their formation and evolution. And it looks a little bit like this. So I'm just showing a plot here of comparing masses that we measure through combining all of these different techniques that I'm going to get into in a bit more detail. So that top line at the top there, it says dynamical mass. That's kind of a representation of what we might measure using things like radial velocities and astrometry. And again, I'm going to go into this in a bit more detail, but we also compare this against what we measure in terms of the amount of light that we receive from these objects through imaging. And we can compare these against models of evolution of these objects and how bright we expect them to be over their lifetime and how old they are. And what we actually find for a number of objects is that the mass that we measure dynamically versus the masses we derive from models actually don't agree a lot of the time. And so doing this combination of techniques to really understand the mass properties and the atmospheric properties is really important to remove the degeneracies in these kind of models versus dynamical masses. Okay, so then how do we do this? So I've mentioned a few techniques already, and I want to get everyone on the same page to make sure that we understand what different exoplanet measurement techniques I'm talking about here. So the first of those is the radial velocity technique. And this is very close to the heart of the Swiss community, as Michel Mayer and Didier Queloz used this technique to find the first exoplanet around a solar type star in 1995 and won the Nobel Prize in 2019 for that. But how does this technique work? So if we have a star in the middle of a system that's being represented by the yellow circle that we see here on this, and then we have a companion, so that could be a planet, or it could be a brown dwarf companion that's orbiting around that star that we see by that, represented by that blue circle here. As the planet orbits around the star, you know, they're kind of orbiting around one another, but the center of mass is just very close to the star itself. But we do get this slight wobble as the star is kind of tugged by the planet as it orbits around it. And we can measure this because we basically know what the fingerprint of stars looks like. So in that bottom right there, where you see that rainbow that's being shifted, we know what lines to expect in the stars that we observe. And if those lines get shifted to the left or to the right, that can be due to a planet orbiting around that star. And we can measure that. And that gives us a handle on how massive that planet might be that's orbiting around the star, and how long it's taking for that planet to orbit around the star, or what's called its orbital period. So the orbital period of Earth is 365 days, but you know, we can measure the orbital periods of other planets using this technique. The other technique I'm also going to mention is astrometry. So astrometry is similar in the way that it's an indirect method to observe exoplanets. So with the radial velocity technique, in the same way that we don't directly see the planet, but we see the effects of a planet in the system, astrometry is similar in that regard. But in this regard, it's more in the spatial plane. So what we do is we observe a path of a star across the sky over many, many years. So the stars move through the galaxy, which is what this linear path that we see here is. And then we see this kind of spiral effect over many, many years. And that's due to the motion of the Earth around the sun, so our own position within the solar system. And so we know where to expect stars at certain points across the sky. But if there are any perturbations from this, which you can see from this orange-brown color here, there can be a similar thing where there could be a companion, a brown dwarf companion, or a planet that is orbiting around that thing and is tugging the position of that star relative to where we expect it to be. And so we can use this information to also decipher what kind of object might be orbiting around that star. And we can combine this information with the radial velocity information to remove degeneracies of the orbital parameters, which can lead to dynamical masses, and remove those model dependencies on deriving those masses. So in order to do this, I primarily use astrometric data from 2 ESA missions. So Hipparcos was a ESA mission about 25, 30 years ago now. And we have data in the archives from that, from the early 90s that we still use. And we need this really long time baseline of data to really be able to do this well. We also have Gaia, which is another ESA mission that's an ongoing ESA mission. And we can use this very long baseline between these missions to really look at the astrometry and see if there is a companion that's orbiting around a star that's causing an astrometric acceleration. And so in this plot here, you can see that there is a point from the early 90s, that's the astrometry measured from Hipparcos. There's a point in 2015 that's measured from Gaia, but we can also measure the difference between these to give us hints of astrometric acceleration if there is a companion orbiting around a star. And so this is another very powerful technique to do this. And so my favorite way of looking at planets quite literally is direct imaging. And conceptually, this is quite easy to explain because many of us, know the concept of being able to take an image of something. But this is not an easy technique because there are many components we have to take into account. So imagine that we have a star and then with a planet or a brown dwarf companion that's maybe orbiting around it. If we take these observations from the ground, then we have to take into account for the Earth's atmosphere. So, imagine like a fan like there, it's very turbulent. There's lots of movement in the atmosphere of Earth. And we can correct for this with ground-based telescopes with what's called adaptive optics. So imagine like here that we see a pair of glasses that's essentially correcting for the wavefront as the atmospheric turbulence causes the wavefront to perturb. We can kind of account for that in real time using very complicated adaptive optics, but we get beautiful images this way. But the other thing that we have to take into account is the brightness of the star compared to the brightness of the planet. And this is really extreme. It gets compared to trying to take a photograph of a firefly next to a lighthouse at like 100 miles away. And so that's kind of how difficult we're talking in terms of contrast level here. So we use what's called a coronagraph that's being represented here by the woman's thumb, kind of trying to remove the light of the star, because when we do direct imaging, we're not necessarily interested in the starlight itself, we're interested in what's around it. And sometimes that could be a disk, a brown dwarf, or in this case, we're talking more about exoplanets, and then that's fed into a detector, like a camera, on board a telescope. And so this is kind of conceptually what direct imaging is. And so the techniques that I mentioned before, so like radial velocities and astrometry, those are really powerful to select targets that are ideal for direct imaging, essentially. And so I showed already the GIF of HR 8799, but this is one really beautiful example of more than a decade of data where we see these 4 planets orbiting around this central star. Another really great example of this is Beta Pic that we can see here just before it's going behind its host star. And these are the kind of images that we get from using this technique. And we can really monitor these over many, many years or even decades. The other thing about combining exoplanet detection techniques is we're probing not only a different parameter space in terms of mass, in terms of separation, but also in terms of age. And so imaging typically, so I'm showing a plot here that shows you the age and the distribution of the percentage of detected planets as the age. And imaging, typically you end up looking at younger systems. And the reason for that is when you're taking an image and the object is still hot, so it's very, very luminous, the contrast is much easier to obtain for those younger systems where the luminosity is still pretty bright. And so we're kind of swayed towards those younger systems with imaging, versus other techniques like those indirect techniques like transits, which I'm not really going to mention here, but I'd be happy to answer any questions about transits if people have them, or radial velocities, which I did mention. Those typically favor slightly older systems. And the reason for that is we rely on the observations of the star themselves. And stars, when they're really young, are typically quite active, and that can make it really difficult within the noise to find these kind of planets. Whereas when they're a bit older and they go into the main sequence and the activity tends to die down a bit, then it's a bit easier to kind of observe these systems and look for those indirect traces of exoplanets. But it's complementary that we need to cover different ages and different spans across this histogram that I'm showing here in order to really understand the formation mechanisms involved in exoplanets, which is demonstrated really well with this plot here. So this is showing tracks of evolution of effective temperature as planets age. So you have age on the x-axis there and the effective temperature, or how hot the object is, on the y-axis, and for different masses. And as I mentioned before, the direct imaging companions tend to be really, really young. And so we're kind of really probing this region here highlighted in yellow, which is great because then we can really test these models of evolution in those really, really early stages, where we have these two sort of model dependencies. So the so-called hot start, where we believe that planets kind of form in a large disk, and gravitational instability causes these things to kind of collapse in on one another and form through that method, versus core accretion, which is kind of the upwards model or the cold start model, where things kind of accrete, the material accretes onto these exoplanets in order to form. And if you capture them in their really, really early stages, then we believe that we can start to decipher between which kind of models the formation mechanisms are favoring. So one analogy I really like to use for combining all of these techniques together is, imagine that you're baking a cake and that these different kind of exoplanet detection techniques are different components of that cake. So maybe astrometry might be the eggs, you have some sugar in the form of radial velocities, you have some butter maybe for direct imaging, et cetera, et cetera. And what's been happening in the community is kind of this, essentially. We take one technique, we measure something, and we say, hey, we've nailed it. We understand this exoplanet completely through this one technique. And this is just not true. We do not have enough information from one data point or from one technique in order to really understand the thing that we're looking at. And so basically, in order to go from that horrific looking cake to something that's beautiful and delicious, we need to bring together as much of this information as possible to really probe a wide parameter space and to really understand the exoplanets that we detect. So here is a plot with all of the detected exoplanets to date taken from the NASA Exoplanet Archive. And different colors are just showing how they were detected through different techniques. I'm showing the kind of like 4 main techniques here, but we do have some others that I am not showing just the simplicity here. So on the x-axis, we have the semi-major axis. So basically how far away the planet is from a star. So in imaging, that would be like the angular separation, or in radial velocities, we would talk about the orbital period. And then on the y-axis, we have the mass of the planet. And what you can see is that different techniques tend to favor different areas of this parameter space. So with imaging, it's far easier to look at things that are far away from the star and are much more massive. So we see this kind of pink region at the top. But then we also have planets that are much closer into their star that are more favored by like the transiting or radial velocity technique, for example. So the planets I'm particularly interested in are ones that are kind of sort of in the middle of this diagram here, and kind of in the further reaches. And the reason for that is when trying to combine a lot of these different techniques to really understand them and to remove the degeneracies that exist in these models. So for the sort of long period radial velocity ones that I've highlighted in yellow there, you know, over time, as we observe radial velocities for a longer period of time, as, you know, this technique is only a couple of decades old for the use of exoplanets, at least, you know, as we start to observe these radial velocities out for more and more years, and we start to probe out to longer and longer semi-major axes. And then on the other side with imaging, as we go to more advanced technologies, more sophisticated data processing techniques, we can start to probe inwards on that semi-major axis and get closer to the star in terms of our capabilities, and also move down in terms of mass, in terms of the contrast level that we're able to achieve with both ground-based instrumentation as well as space-based. And so what's happening over time is we're kind of merging these different exoplanet detection techniques together. And like I said before, that's really powerful because that removes the degeneracies of unknown orbital parameters and model dependencies, and really allows us to understand the exoplanets that we're looking at. And a technique that I also mentioned was astrometry, and I'm going to very broadly put astrometry on top of here because we're sort of in the beginning of the era of really starting to observe planets using this technique, but this is also going to span sort of this approximate mass separation parameter space here, which again, you can see kind of overlaps with that parameter space that I was showing before, and be a really powerful technique. Okay, so how am I doing this, and how is this all sort of coming together? So I mentioned before about the radial velocities, and that gives us access to the minimum mass of the planets that we're looking at. And the reason for the minimum mass is that if we only have the radial velocities, we do not know the orbital inclination of the system. And so it has a dependency on that. But it does give us a minimum mass of the planet, and that's already very powerful. It also gives a handle on the orbital period, so the semi-major axis, or how far away the planet is from the star. So that's really useful information for its orbital dynamics. Then the astrometry that I mentioned, if you combine that with the radial velocity information, if we have access to both of those things, means that we can remove the degeneracies and actually get access to those dynamical masses, those model independent masses of the planets, because we're able to fit for the inclinations of the system, and we're no longer talking about a minimum mass, but we're talking about a real true dynamical mass. And then combining that as well with imaging, which gives us further orbital constraints, so we can get even more precision on the mass. But importantly, it also gives us access to spectral information because we can directly observe the emission spectra of these objects and actually start to decipher their atmospheric properties. So this is excellent because then we have information about how far away this planet is from its star, how massive this planet is without depending on models, but also what's going on the planet itself. And so all of this leads to comprehensive characterization of these cold gas giants. And the reason for that being is that these are ones that are favored by imaging. So they're far away from their star, they're pretty massive, and they're reminiscent of Jupiter and the outer reaches of our solar system. Okay, so the way that I've been doing this and that I'm going to talk about today in this talk are using these different components for the different measurement techniques. So I already mentioned before of Astrometry that we have 2 ESA missions that have been really powerful to provide us with astrometric information, and that's Hipparcos, which is no longer on Sky, but we still have a lot of extremely interesting, useful information from the archive from Hipparcos that was around in the 80s and 90s. Gaia, which is an ongoing ESA mission, and that we're still getting lots of really great information and data from Gaia. On the radial velocity side, I'm going to primarily talk about today about radial velocities that come from the Coralie survey, which is very apt talking to people in Bern, because this makes use of the Swiss telescope. So I'm going to talk a little bit about that. And then I'm going to talk about some of the imaging results using some of the European Southern Observatory or ESO VLT results, primarily with SPHERE, but I'll also mention some interferometry as well at the end. And so these are the kind of things that I'm putting together to really understand these objects. So I mentioned the Coralie survey, and you can see in this beautiful image here, this is Lucia Observatory in Chile, and the Swiss telescope is on the right there, and the one on the left in the background there is where Harps lives as well. It's also a very powerful instrument to get radial velocities, but I'm going to talk primarily about Coralie that sits on the Swiss telescope. And the Coralie survey, it's an ongoing radial velocity survey. It's being led by people at the University of Geneva. We have data from more than 20 years of radial velocity data now, and it was a volume limited sample of stars within 50 parsecs when the target list was first generated. It contains more than 1,600 primarily main sequence sort of G and K dwarfs. And the ones that we've been sort of pretty interested in looking at for the purpose of imaging is to look for radial velocities that show long-term drifts that could host potential companion candidates that would then be amenable to look with direct imaging. And so for a number of these companions, if I take you back to this mass separation plot that I showed before with the exoplanets, had a number of these where we have these like long-term trends in the radial velocities that we've seen in the Coralie survey. And these ones that I'm highlighting here in the middle were ones that I published in 2019, so a few years ago now. But you can see that they sit right at this boundary between the ones that we're able to detect with long-term radial velocities, but also potentially in the parameter space that we can detect with direct imaging. And so these are really exciting. And this wasn't super intentional that we have these ones here, but these were the ones that we were kind of following up of these sort of long-term trends. And what we also found was that, so this is a plot from the same paper, and we looked at the metallicities of the stellar hosts of the systems, and we found that most of the stars of these systems had what's called a metallicity excess. So they have a lot of material that's essentially not hydrogen or helium, and this kind of agrees with the theory that giant planets are expected to form around stars that have a high metallicity. And so that's what we're seeing here. That black line in the middle is the sort of solar metallicity, and to the right of that shows that we have stars that are more metal rich than our sun. So I've been mentioning combining all of these different techniques. I'm talking about the radial velocities here. But if you fold in that astrometric data that I've been talking about, so the Hipparcos and Gaia information, you can do orbit fits, and you can see how you expect the companion, the planet, to orbit around its star. And that's what I'm showing here as a result of a prediction of a map of where we might expect a planet to be relative to its star. So the blue cartoon star there is actually where the host star would be. And then the contour lines that we're seeing is where we expect a planet to be relative to its star. So this is before we've done any imaging. This is just with radial velocities and astrometry. And the reason why this is so important is it actually enables us to predict whether we expect a detection with direct imaging. So previous imaging surveys just relied primarily on basically blind surveys that weren't necessarily super successful in actual detections of planets. Whereas using these techniques and this precursor information actually enables us to make informed decisions about whether it's worth spending our telescope time looking at these targets with imaging, and whether the planet is in a parameter space that we can actually measure. And so this has been really, really important for the detection of exoplanets using imaging. So the way that we assess this, so what we're seeing here is as a result of the orbit fit. So that tells us about the separation away from the star. And then we can plot this sort of separation on top of what's called a contrast curve. So here I'm just showing an example contrast curve from the isochrones, which is just some models. And so the contrast is just like how extreme is the mass ratio between the star itself and the companion. And the separation is just how far away is that companion from the star. So we have that information from the orbit fit that I showed in the previous slide. And then we also get an estimate of the mass from that data as well. From the radial velocity and astrometric data, do the orbit fit, we get an estimate of mass. We know, or we have an estimate of the mass of the star. So that gives us a prediction of the contrast. And then we also have a prediction of separation. And if that prediction sits underneath the contrast curve within this pink region here, then that essentially means that this thing is unlikely to be detectable, or at least not a strong detection, and that maybe we should just, maybe not spend the telescope time observing that object. But to the contrary, if it's above that line or above this kind of gradient, then that's a really powerful argument that we should be spending time imaging these objects. So I mentioned before for the imaging component that I primarily have made use of the European Southern Observatory's VLT and primarily with SPHERE, which is an imaging instrument that sits on UT3 that's been highlighted there. This is at Paranal Observatory in Chile as part of the European Southern Observatory. And for those of you that don't know, SPHERE has capabilities to do what's called like simultaneous imaging. So there's two components to SPHERE. There's IRDIS, which is an infrared dual band imager and spectrograph. And this allows for narrowband imaging across the Y, J, H, and K bands. But at the same time, so not costing us any more observing time, we can use what's called the IFS, the integral field spectrograph. So I mentioned before about being able to do some spectroscopy with these. We can observe using IRDIS and IFS on SPHERE simultaneously. So that gives us access to some of the spectral information of these objects, and that's really powerful. Okay, so one such object that I will highlight from the detection from the Coralie survey is HD 13724, and I will re-emphasize that this is really 20 years worth of data, so these radial velocities are huge. When this was published in 2019, we had only the minimum mass, we had only the radial velocity, so we didn't know the orbital inclination. And we predicted the minimum mass to be about 27 Jupiter masses. So this is a brown dwarf, which, are really great analogs for cold gas giants in order to understand the atmospheric properties. So then we went ahead and imaged it. And in 2020, we published these beautiful detections that we can see here. So these are just images across different narrowbands in the H band. And you can see, so we have the star that's hidden behind that coronagraph that I mentioned at the start, that's masked out by that white circle there. But we see the companion next to the star, and you can see it really clearly in these images. And showing here, this is using what's called angular differential imaging as well as spectral differential imaging to get these detections. We then took some follow-up imaging to confirm its orbital motion and to really constrain the properties of what we were looking at. So we have some follow-up in a J band. So again, this is narrowband imaging, but we're using a different filter in this case. And we can see the companion really clearly again across those bands. And we can see even that it's moved a little bit, which is great because that gives us access to even more orbital constraints on the parameters. And again, we took some other follow-up images, and again, this time in the K band. And the K band's at longer wavelengths, so you start to get more thermal background and starts to get a little bit noisier. So you can see that there's a few more speckles, those sort of other bright spots that we can see in these images, and that's just due to going out to those longer wavelengths. But we can still see where the companion is, and that agrees with where we expect it to be on the images compared to the other images that I showed you before. So this is really great that we have all of these images and we can combine all of this together. So we have the H, J, and K that I'm showing here across 3 different epochs, along with the radial velocity information, to give us a dynamical mass that does not rely on models. And this is really powerful, and this is what we can gain here. And then in order to pull out the spectral information, What I'm showing here are the sphere data, but across wavelengths. So x-axis there, we have the wavelengths. And the gray narrow bands correspond to the images that I just showed you. So those are the photometric points corresponding to the ERDIS data, the narrowband J, H, and K. And then we have this pink region that is covered by the IFS region. So I mentioned the simultaneous capability. So this is the kind of information that we can gain, and we can fit this against models in order to really understand what we're looking at. And this object is around 1000 Kelvin, and we can compare this against models to see if there are any discrepancies in the things that we're measuring. We see a slight flux excess in the K-band that could be due to clouds that are not being correctly accounted for within the models. So that's quite interesting. And, you know, this is a really great object to kind of continue to follow up. We can also make a comparison against more high resolution data of brown dwarfs that are like free floating, for example. So what I showed you before was the fit against some models, but we can also fit against other observed objects that are similar to what we're looking at. So again, we have the IFS and the ERDIS gray narrow bands, and we have fits to objects that are sort of a mid-T type, T4 type brown dwarfs around 1000 Kelvin. So that kind of agrees with the models that I showed you previously. And we can see these kind of absorption features due to these atmospheric properties. For example, here we're seeing a lot of methane and a lot of water, which is what we kind of expect for a mid-T type brown dwarf. So I mentioned at the very, very beginning that we can measure the dynamical mass and compare these against models. And some teams like the figure I'm showing here is from Brantatel 2021 have kind of done this across a number of different exoplanets and brown dwarfs to really understand the models and, you know, what we're really looking at here. And we can see that there are a number of brown dwarfs in this parameter space. We have the age on the x-axis, how old the system is, but also the mass on the y-axis. And some systems are consistent with the models, but we also find that some objects are overluminous and some are underluminous. And so Brantatel actually came to this conclusion that sort of younger and lower mass brown dwarfs are typically overluminous compared to models, while older or higher mass brown dwarfs are underluminous. And so it's really important to understand the mass properties of these things that we're looking at, and to compare them to models to kind of refine what, you know, why this may be the case. And so for one such object, they also looked at the same brown dwarf I mentioned before, and folded in additional astrometric information and was able to decipher a new dynamical mass for this object. And again, this just shows how powerful it is to bring all of this information together. And I'm showing the orbit fit here, and you can see just how well the orbit is constrained of these objects compared, you know, by combining all of this information together. So using these orbit fits, I mentioned before, we can use it to predict whether we can image these things or not. So I'm going to show another example of this. So we have a whole zoo here, and these are some objects that I published last year. And these are all from orbit fits. So what I showed you before is an orbit fit, and we can use these contours to predict where these objects are relative to their star. So the blue stars in the plots that you can see those in, that's the host star. And the dark red color, that's where we expect the planet or the brown dwarf to be relative to the host star. And so we do these maps first, and then we put them onto a contrast curve. So I mentioned before about this, you know, if it's under this sort of pink barrier that I mentioned previously, then we maybe don't want to spend too much telescope time on those. But you can see here I'm just showing the contrast curve again, and these are from measured on-sky performance from Sphere for 5 sigma contrast curves that are stacked. The lighter, whiter colors, those are more likely to be directly detectable using imaging, and the darker colors are less likely. And for these objects that I published last year, you can see in this case that we're well within that regime of being able to detect these using those orbital predictions that I just showed you. And so this is a really powerful way to demonstrate that we should be using this telescope time to really constrain these kind of objects. So this led to a really great zoo of detections you can see here. So again, this is using data from Sphere on the VLT. And what we can see is we have the central star in each case behind that white circle. And then we have the bright companions that are orbiting around. And you can even see in one case in the bottom left there where we had a triple system that we even observed. So we had 2 companions that are orbiting around. a central star. So using, this information, this is really powerful for target selection for these things in order to really understand them. And if I bring you back to the predictions versus what we measured, this is where we're at. So the contours, the dark reds, those are the colors where we expect to be able to actually observe these particular targets. And then the gray cartoon stars on top, those are where we actually observe them. And so you can see that we're really in a really nice space where we're actually getting the detections on top of the orbital predictions of where we expect them to be. And so this is really powerful in terms of actually measuring the mass of these things, measuring their orbital properties, and actually getting these detections and increasing the detection efficiency of direct imaging of exoplanets and brown dwarfs. And another sort of cautionary tale to the community about understanding dynamical masses is this example that I'm going to highlight. So HD 92987 was what we thought was an exoplanet that was published in 2019 by myself. And at the time when I published it, I had a mass around 17 Jupiter masses or so. So, either a very, very giant planet or potentially a low mass brown dwarf. And again, this is a cautionary tale that this is the minimum mass at the time. We didn't know the orbital inclination. This is just with the radial velocities. And you can see the radial velocities on the right plot there that I'm showing. Then in 2021, Veneratel folded in astrometric information into understanding the dynamical mass of this object, and actually found this object to be much more massive than what the radial velocities had led on to be, and was actually more like 256 Jupiter masses, which is a low mass star. I then went ahead and actually imaged this object and folded in this astrometric information from the imaging, and confirmed kind of what Veneratel had said, that this object is, a low mass star. And you can see the orbit fit on the left there that I'm showing, and we have this really beautifully constrained orbit fit. But the reason that the true mass is so much more massive than what was derived from the radial velocity minimum mass is that the orbital inclination of the system is close to face on. So it's like this, instead of looking at a system like this, it's really orbiting around and a face-on orbit. And this is my huge cautionary tale to the community, is to, minimum masses are not true masses, and to not just trust the radial velocity masses that we have of planets, and why it's so important to combine all of this information together. And obviously getting detections of low mass stars is important and interesting in itself, and there's a lot of fundamental science to be learned through that. But if your aim is to understand the exoplanet and brown dwarf population, then this is clearly not an object that falls into that category. And this was an object that at some point lived in the NASA Exoplanet Archive, and now no longer does, because it is debunked that it's not actually an exoplanet. And so this is really important for us to be able to do this and to understand what the demographics of exoplanets look like as well. But then one really neat thing that does come from doing this is we can, get detections of these kind of low mass stars and start to pin these against, stellar models as well. And so this is kind of a nice result of doing that as well, is kind of putting them against different stellar models and understanding what we're looking at that end of the spectrum as well. Okay, so two new objects that are very soon about to be submitted, actually hopefully this week, two new benchmark brown dwarfs that we have through using this combination of techniques. So here I'm showing the radial velocities of two new objects, HD 206505 and HD 112863. And you can really see just how beautiful these radial velocities are. We have really nice orbital phase coverage. The different colors of the data points there just correspond to the different upgrades of the Correlate instrument that I described earlier in this talk. But you can see that these radial velocities are really well defined, and that gives us access to a really precise mass from looking at these things. And again, to come to those astrometric predictions in their orbit fits, what I'm showing here is, again, the blue star corresponds to where the host star is. The red contours correspond to where we predict those objects to be relative to the host star. And the gray star corresponds to where we actually detect these objects in imaging. And as you can see, those radial velocities give us such a wealth of information that at this point, we are just so spot on, which is really, really exciting to see. So this is what the result of those images look like. So in the top there, showing the 206-505 one. Again, this is with sphere data. So we have both narrowband imaging, both in the H band and the K band. So, having access to more than one epoch also gives us additional information in terms of wavelength coverage, but also in terms of orbital parameters over time. And then in the bottom one there, I'm showing 112863. And again, we have detections both in the H band and the K band. And we can actually see in that case it's moved a bit more than the other one. And it's also super, super close to its star. So again, the white circle corresponds to where the star is. And it's so close to like what's called the inner working angle of the coronagraph that we've even had to take into account for the chronographic transmission at that point, because it's not a 100, we're not receiving 100% of the light because it's so close to where the coronagraph sits. And so that's been kind of a factor to take into account as well. But these are, so I'm showing here the orbit fits with the radial velocities. So I showed you the radial velocities before, and then combining all of this information together. So the radial velocities, but also the astrometry is folded into here. So the Hipparcos and Gaia information, as well as the astrometry from the imaging that I just showed you across these two epochs, gives us access to these absolutely beautiful orbit fits that we can see. So in the top there, again, I'm showing 206-505, both the radial velocities and the orbit fit, and 112863. And this just has a really beautiful orbital phase coverage across the whole thing that we can see. And this gives us access to this kind of brown dwarf mass regime. So these are really at the stellar substellar boundary. So really sort of in those high 70 Jupiter mass objects that really sit between this regime of what's considered a high mass brown dwarf or a very, very low mass star. And so they're also really exciting for this reason to try and understand their atmospheric properties as well. So then that kind of leads me on to looking at the spectra. So Will Traver, who is a PhD candidate at the University of Geneva, so in Switzerland, has been looking at some of the spectroscopic follow-up of these objects. And this is just very preliminary analysis at the moment. So take this with a little bit of a pinch of salt. But we see from its color magnitude diagram of the colors that we get from both the H and K band and what its spectra is from the IFS sphere data, that we think that these are kind of early L-type objects. And they're both actually pretty similar in spectral type. So that's quite interesting as well. But Will's working on this paper, and so stay tuned for that coming soon, hopefully. But again, this gives us a lot of access to really important information to understand atmospheric properties. I know that I'm talking about brown dwarf companions here, but the overlap between brown dwarfs and giant planet atmospheres is, very, very closely overlapped. And so, but it's easier to detect brown dwarfs just because they're more massive. And so if we're able to detect brown dwarfs and understand their atmospheric properties, that helps us really understand the atmospheric properties of giant cold gas giants as well. And then taking this even one step further, a technique that I won't go into in too much detail, and I haven't mentioned yet, but it's interferometry. And interferometry gives us access to yet another parameter space. And so this is work that's being led by William Balmer, who's a PhD candidate here in Baltimore at Johns Hopkins University. And we have some gravity data. And so gravity is an instrument that also sits on the VLT, where Sphere also is, and gives us access to interferometry data. And so interferometry is another direct detection technique, so much like in the way of direct imaging, but we can look even closer to the host star, which really opens up a whole other parameter space. And it also gives us access to medium resolution spectral information out to that K band, to those longer wavelengths around 2 to 2.2 microns that I've highlighted here. And again, this is preliminary, but we see that this beautiful coverage, the spectral coverage that we have from the sphere data on those shorter wavelengths that's been highlighted by the blue points and the photometric points that we get from sphere, along with that red spectra out at those longer wavelengths. And this is really key in understanding all of the spectroscopic properties of these objects that we're looking at. So not just a narrow window and not just images, not just photometry, but actual spectral information. And again, we see really nice features in this, like hints of, methane and water and potentially even sodium as well. So again, stay tuned for that as we kind of establish and look at more of these objects using interferometry as well. So in my last sort of few slides, I wanted to mention the James Webb Space Telescope. So I am based at the Space Telescope Science Institute in Baltimore, which is home to the Missions Operations Center for JWST. It was launched by the European Space Agency in 2021, so I'm very proud to work for ESA, and it was a really successful, amazing launch. And this is the last image that we have of JWST before it went out on its long journey to L2, 1 million miles away from Earth, where it currently resides. And the JWST is just opening a whole other parameter space in what we're able to do in exoplanetary science. So I mentioned before about probing out to those longer wavelengths with interferometry. Well, JWST is going out to even longer wavelengths, and that is opening up a parameter space and really sending our theorists and modelers down a rabbit hole in order to understand what's happening at those longer wavelengths that we just haven't really had access to at this level of sensitivity, this level of resolution, until JWST came along. And so in terms of imaging capabilities, we do have chronographic imaging both on NIRCam, which is the near-infrared camera, and also MIRI, so it's a mid-infrared camera. And we can see some of the stats here from Aaron Carter's paper, who did some simulations just before JWST was launched. And we are seeing that the simulations are in agreement, and actually we're performing even better than what these simulations were provided to us. But we're really getting down to that mass regime now of, I know I've been talking about sort of a lot of brown dwarf companions or very, very massive planets, but we're starting to, get that capability where we can get down to sub-Jupiter masses within like within 30 AU as separation between the star and a planet, sub-Saturn even at sort of 50 AU, and even down to potentially 0.1 Jupiter masses beyond 100 AU. And so this is just super, super exciting in terms of the capability that JWST is starting to bring to us. And we're already seeing this in the first year of science with JWST. But, this is just the beginning of the journey of what JWST is enabling. And so I wanted to highlight the first direct image of an exoplanet with JWST. So this was HIP 65426. This was a planet that had been previously detected with SPHERE, in fact, on VLT that I've been talking a lot about today. But we wanted to select a star for this program. So this was part of the early release science program. We wanted to pick a planet that was, already known about, so that we could measure the true capabilities of what JWST can do. And so what we're seeing here are imaging across different filters. So there's 4 images there. The 2 on the left are showing that near-infrared camera image, and the 2 on the right are the mid-infrared. And you can see just how, there's sort of the PSF of the near-infrared images versus the mid-infrared, and how the colors kind of change. The white star corresponds to where the host star is, and we're seeing that kind of blob there, that's the planet. And this was just really our sort of first look at the chronographic capabilities of what JWST can do, and kind of opening up, a new era of imaging with JWST. And it's going to be super exciting to be able to, get more, especially more of those mid-infrared images that we just haven't been able to do with any other instrument, either from the ground or space before. So stay tuned for more exciting imaging capabilities. But the thing I really, really, really want to highlight, which is the last result that I'm going to talk about, is an object called VHS 1256. And, images are really exciting, and it's really great to see these things. And we also have images of this object, but not only an image, but the first direct spectrum of a planetary mass companion with JWST. And this has just blown us away in terms of the resolution and the capability of what we're really seeing here. And so I'm just going to, highlight some of the amazing molecules that we're seeing in this amazing spectra here. So we have water, we have methane, we have carbon monoxide, we have potassium, sodium. But for the first time ever, we've directly observed silicate clouds in a planetary mass companion. And it's highlighted in black there out at a sort of like 10 micron wavelength range. And this is the first hint of silicate clouds in a planetary mass companion that's been directly observed. And we needed JWST to do this because of that wavelength regime that we have not been able to probe at this level of resolution before. And so we have many objects for which we're looking at, which are also giving us fruitful, really exciting results that I can't wait to share with you in the near future. But this is kind of, I think, just an incredible way to end this talk of saying, like, this is the next generation, and I'm super excited to see what comes. And so with that, I will just put up a couple of sort of roundup summary points. So, you know, we're helping to understand the occurrence rate of what these exoplanets, brown dwarfs, and even low mass stars looks like around solar type stars, and understanding these mass luminosity relations. These precursor information, so the radial velocities and the astrometry that I mentioned, are really important in increasing detection efficiency for direct imaging of exoplanets. And the overall point to take away from this is that combining all of this information together is super, super important. It's vital in comprehensively characterizing exoplanets. And so if you have any questions, I'm happy to take them. Thank you.
Thank you, Emily, for the very, very informative and inspiring talk, especially the cautionary words about not using a single technique to derive, you know, fundamental parameters. This is a lesson that I think many of us have to learn. Sometimes you trust just one tool, and that's never doesn't never give you the complete picture. So for the audience, if you would like to put your questions in the chat, we can go through the questions that we have so far. I will call the person and unmute their phone so they can actually read it. So the first person asking was Hugh Hudson. You should be able to talk.
Right. I just wanted to ask how well ALMA could help with the planet search.
Yeah, so ALMA is definitely really powerful. Because of the wavelength range of ALMA, it's typically better to look for disks for around objects rather than for maybe point sources that we see in sort of the near infrared. So ALMA focuses more on like the millimeter wavelength regime, and that's really great and complementary to what we do to look for like protoplanetary disks and debris disks and this kind of thing, but it's not quite the right wavelength range to look for a lot of the planets that I've shown here. You can see maybe really, really young planets as they're accreting within a protoplanetary disk, but not the sort of point sources that I've shown here that are already established and are no longer accreting.
Thank you very much. The next question is from William Wall. William, you should be able to speak.
Hello. Yes. I think you've already partly answered my question, but maybe you can go into a bit more detail. It's about the work you're doing on exoplanets must in some way, or at least sometimes, constrain some stellar models of the host stars.
Yeah, exactly. And this is kind of like a really nice byproduct of what we're doing. So, you know, it's one person's trash is another person's treasure kind of thing. That's, you know, not to call stars trash, of course, but when we get these detections, it's really actually great because then we get precise dynamical masses of these stars as well, which is something that people that work more in sort of the stellar community is something that they also really want to understand, the fundamental parameters of these things. And so we're able to look at things like mass luminosity relations and what the occurrence rate and what the binarity of these kind of systems are. And that's still really useful information for the community at large, but also for the stellar community to perhaps follow up these objects in more detail as well. So absolutely, we get a lot of wonderful information about the stellar parameters and also of the host star as well, because if we measure their radial velocities, we get high resolution spectra of these stars, which can help us understand their metallicities, can understand their ages and their masses as well. So yeah, lots of information about the stars as well.
Have you found any surprises in the stars?
Yeah, I mean, I think like one of the relations that I spoke about in terms of the metallicity excess versus the masses of the objects that form around these kind of stars, like that was something that wasn't really known, wasn't really thought about until we started to establish this and observe more of them. So things like looking at metallicities has been, I guess, a little bit surprising. And really being able to just constrain those mass luminosity relations. So I did show one in the talk, and We have a few stars where they're kind of maybe underluminous compared to what we expect for their mass luminosity relation. And that's usually a hint that there's something in the system that we're not seeing. So usually like an unresolved binary, for example. And so those can be quite surprising, and there's really no way to directly detect that. So actually getting these precise masses is really important for that.
Yeah, thank you.
Oh, Antonella, I think you're muted if you're trying to talk.
Thank you. New question from Ganesh Nathan. You should be able to talk.
Yes, thank you for the excellent presentation. One of those slides, that the last one, not the conclusion. Before that, you showed about this all the gas compositions like the H2O, CO, things like that. Not this one, the one before. Yeah. So I'm just wondering. I'm very new to this one, but I'm disciplined. I'm an engineer, not an astrologist, astronomer, but I am interested in this. So I would like to know whether this there's no, you have identified CO but no CO2. Would that be some kind of sign for life forms as we have on the planet Earth? I'm just curious about it. What's your thought on that?
So I didn't mention CO2 in this spectrum, but we do see hints of it. We don't see enough of it to really claim that we see it, but it's likely that it's there. And in the paper, we do some models where we compare against what the spectrum would look like with it versus without it. And it's showing hints that it's likely that there is some CO2 there. It's not strong enough to say that CO2 in itself or any of these molecules in itself are potentially signs of life. We're still trying to understand what biosignatures or so-called biosignatures we'd need to look for to really define what would be a sign of life. Because some of these molecules could be produced from potentially even the planet themselves. So like geological activity, for example, we see that on planet Earth. So we have to really define what a biosignature is, and CO2 in itself is not enough to say that we see signs of life. But we do see some hints of CO2 in this spectrum. And I believe that this object's going to be followed up at some point. So, and not just with JWST, we also have Hubble Space Telescope observations as well. And so we will continue to really understand what the things are that we're looking at here.
Okay, thank you.
Thank you, Emily. We have a hand raised by Jordi Miraldes today. I think you are now allowed to speak. Let's see if we can hear you.
Yes, thank you very much for your talk. I actually wanted to ask also about this wonderful spectrum. So wanted to ask how many exoplanets do you think JWST will be able to take similar spectra of, to be able to tell, how much variation there is in the properties of the spectra among different exoplanets?
Yeah, that's a great question. So JWST's already really looked at an abundance of exoplanets and brown dwarfs as well. And a lot of these objects, we do have, a similar level of detail of the number of molecular features that we can see here. Another technique that I didn't go into too much detail is the transit technique as well, which JWST also has capability of. And so people also work on the transmission spectroscopy of those kind of objects. And that can be quite difficult because you have to account for the star itself as well. But people are also looking at the spectroscopy of these objects. But I do believe that for the vast majority of exoplanets that we'll look at with JWST, we'll be able to get to this level of detail, which is super exciting because we've not been able to do that before. And, the more of these that we look at, the more we'll be able to really understand, as you put it, the variation, the diversity of the number of different exoplanets we have, and really start to understand what their atmospheric properties look like across different temperatures, across different masses, both rocky planets. I'm talking here more about gas giants, but also rocky planets as well. How many we look at exactly will depend on many factors, like how much observing time we get and how long JWST will live for. But hopefully, the more, the better in order to really understand these objects.
Thank you.
Thank you, Emily. Another question, Andrew Lazarevic. You should be now allowed to talk. Let's see, we can hear you.
Okay. Well, thank you very much. Fascinating talk. I'm very intrigued by the silicate clouds that you were describing. Silicates are typically surface materials or something close to surface material. Does this give you any ability to look down into the atmosphere, like considerably further down?
Yeah, that's a good question. So I guess the way that we interpret the silicates here is that they're within the sort of clouds of the planetary mass companion that we're seeing, and they're potentially kind of swirling around in the atmosphere. So think similar to what we see with, like, you know, Jupiter, for example, that we have these kind of cloud bands. Seeing down to different layers of the atmosphere is going to depend which wavelength regime that we look at. So that's, again, why it's really important to have this wide wavelength regime, because that will give us access to different layers in the atmosphere that we're looking at. But we don't believe, you know, these are sort of like, these silicates are within the sort of, you know, atmospheres of these things are kind of swirling around in that sense. And exactly the composition of the silicates is something that we're now working on. We have some grad students at Johns Hopkins who are actually doing some really great work to understand what the exact composition of those silicate clouds potentially looks like. And so stay tuned for that as well.
Well, very interesting. Thank you very much. Just there's plenty of food for thought here. Thank you for a great presentation.
You're welcome.
Thank you, Emily. Fascinating talk. I will take the last question for myself and say, you have shown us what JWST can do, and this will be the future for exoplanet science for the next decade or so. But there is a lot of talk, especially in the US, about a possible successor to JWST. This is the Habitable World Observer. So can you just give us a preview of what that one will do and how this already beautiful spectrum will evolve with the HWO? And also, I know that there is a lot of talk of Europe getting involved. So how do we do to make that happen?
Yeah, so the Habitable Worlds Observatory, or HWO, is going to really focus on reflected light of direct imaging of exoplanets. So what I'm showing here from this spectrum, and it's actually nice that we're on this spectrum right now, is emission spectra. And so that's from directly observing the emitting light from bright luminous objects. And that's typically why we look at sort of giant gaseous planets, because they're more massive and they're more luminous. Whereas HWO is going to focus on reflected light. So the light gets reflected from, you know, from the host star onto the planet, and then we observe that reflected light. And that means that we'll get access to a different parameter space, more like terrestrial planets, so rocky planets like our own planet Earth, that are much closer to their star. So really things that reside in the habitable zone of those objects and are more like rocky. And so this will be the mission that will really be looking for those signs of life that we mentioned just before, and what those potential biosignatures may look like. There's even been discussions of looking for ocean glints and rainbows of terrestrial planets with HWO. And so it's going to be really exciting in what we'll be able to probe with that. So the main differences is we'll be looking at a different population of planets, more like rocky planets, and things that are much closer to their star, and looking specifically for potential signs of life. In terms of, you know, how Europe can get involved, I know there's already a lot of buzz in the European community in terms of both science, but also technology development. There's a number of really great optics labs that are working on chronographic technology development. You know, this is not going to be an easy task to get down to this contrast level that we will require to do reflected light observations and to look for these kind of molecular features and this kind of level of spectroscopy. But, you know, also on the science side as well. And in terms of getting involved, there is a plan for the European Space Agency to put out a call for members of the European community to be ex officio members of what's called the START team. And so that call should be going out relatively soon. So if you are involved either in the science or technology of you know, direct imaging of exoplanets, then we will want to hear from you. And I think that will be a really great first step in the European involvement of this mission. And I'm very excited to see what's going to happen with that.
Fantastic. Let's thank Emily again. We can only have virtual clapping, unfortunately. Thank you so much for being my wonderful speaker today. And to the audience, thank you so much for listening. Stay tuned for our Game Changer seminar on the EC website. You will find next options to see beautiful new results. So thanks again, Emily, and thanks everybody for attending. Goodbye.